So this is the most crowded day so far of our workshop, and the first speaker is Sharmodeep Bhattacharyya from Oregon State University. There's the title.
Hi, thank you for inviting. My talk is quite a recent work, so we have just submitted this work. It is not up in archive yet, so if you want a preprint or anything, just let me know. I will email it to you. So this is work with Sharmodeep Chatterjee, who is in City University of New York math department, and so the work is based on spectral clustering for dynamic block models. And so in the talk I will try to give some motivation about going for the dynamic block, means dynamic network models, and then spectral clustering methods for dynamic network models, and some of the theoretical results we could derive for the spectral clustering methods for dynamic block models. So the network data, as we have all seen in various talks, is something like usually represented in sometimes represented in graphical format, where it is represented in terms of nodes and edges, whereas the numerical representation is usually in the form of adjacency matrices. So that means the adjacency matrices in the form of adjacency matrices, where if there exists an edge between two different nodes, in that case you have 1 in the adjacency matrices, otherwise 0. So usually it is in terms of adjacency matrices. But we have seen recently, not recently, means networks have always been, means in various cases, that they are either dynamic or time varying. That means there are, when the network data is collected, they vary over time, or we collect several networks at different time points. And this can range for various examples, like co-authorship networks like this one. These are two examples that I just took out from internet. So like this one is a co-authorship network example, where the co-authorship network varied with time. And in this case you can see that not only that the number of edges were varying with time, but the number of nodes were also varying with time. So this the kind of dynamics that goes on in network models that is very diverse. So it can range from like the whole network changing to just some of the edges changing. So like in these cases you can see that there is huge amount of change going on, both from number of nodes to number of edges. Whereas here the number of nodes, this is a neuroscience example where the number of nodes are remaining unchanged, but the structure, the network structure is changing with time. So this is a neuroscience network. But the network that I started with, means based for this problem, was a neuroscience motivating example too, but it was of a different format. So this example came from this experiment was done on human patients, mostly epilepsy patients. So for them, these electrocorticograph arrays, which are sensor type of arrays, are placed surgically within the brain, and based on, and this sensor array collects the brain activation data for something like a month. And after that the array is removed from the brain, and the data that is collected is usually analyzed. So like in this kind of situation in the brain, array, in this case it was 64 cross 64 sensor array, was placed in the brain, and the brain activation of different parts of the brain was collected, information was collected through the sensor array. Now the task that was actually looked into with the help of this, what this is known as electrocorticograph array, was actually speaking. So the speaking is means this electrocorticograph array has the power to sample, means collect instances at a very micro scale, like at microseconds or milliseconds range. So that's why something like speaking can be analyzed with the help of this kind of data. So so the type of data that was the type of activity that was analyzed here was speaking. So the patient was asked to speak monosyllabic words, and the brain activity was recorded during that time. Now based on that, of course, means we tried to construct some kind of correlation network of all these different kinds of electrodes. So we had what we can say a time varying networks, time varying range of networks. So something like, for speaking something like a monosyllabic word, which usually take 1 second, we had close to about 100 different networks collected during that time. So, and our goal somehow was that whether we can analyze that there are certain parts of brain were interacting with each other when performing this specific kind of a task. Now, and that means doing some kind of network analysis after we have constructed this network using the electrocorticograph sensor arrays. So this was one of the motivating examples also that motivated us for this problem. So the problem that we are interested here is something like, we'll go into the details of that, but mostly that we have a series of networks, and we are mostly interested in community detection in the series of networks. Now, this can be done in various different ways and has already been done also in various different ways, but we tried to go for this in a specific format, and trying to define a problem for which we can do some theory also. So, for going into that, let us go into some kind of some kind of myopic review into dynamic network models. Yeah.
How do you go from the measurement to network?
So the measurement to network was done through actually partial correlation measures. So we tried to get the partial correlation of the different electrodes based on the activation, the measurements that we have. So it was a partial correlation network.
The threshold afterwards, or was it a weighted graph?
It was a weighted graph. But actually, we converted into a 0-1 graph for the net, means when analyzing for network, but it was originally a weighted graph.
The subjects had an additional medical reason for having this activity?
Yes, the subject was actually epilepsy patient. So usually this kind of electrocorticograph arrays are placed on epilepsy patient in order to, both for therapeutic reasons also, along with like clinic monitoring reasons. So that's why this array was placed surgically onto them. There is a large literature also on this kind of dynamic network models. So, and it means one of the initial models on network buildings were also built on this kind of dynamical models. So like Baravasian-Albert models or preferential attachment models, this kind of models are all dynamic network models because they were introduced such that the network evolves with time, this kind of framework. But in this kind of dynamic time evolving formation of networks, what happens is that usually the node number also changes with time. Now, in this kind of a situation that we had, our case, the node number, the number of vertices in the network was not really changing with time. It was constant with time. So that's why this is a class of networks or network models that we didn't really look into that much, but there is a huge literature on this class of network, which is the evolving formation of networks. There is another large class of network models that has been proposed, which are based on extension of static models. That means models which are just at one time point, such as for extensions of latent space models, for which several works have been done recently, to extension of mixed membership block models, which has been done by Eric Zing's group and several other follow-ups. There has been extension of random dot product models by Carey Prieb's group, mostly used for detection of change points. And there has been extension of stochastic block models also. One of the works by Kevin Zhu and also Chris Moore here, their group on Santa Fe, they also did an extension of block models. And there has been extension towards this kind of graphon models or Erodosiani models for extension of them towards dynamic models too, by Harry Crane, which was recently also there. So there has been lot of extension of this kind of static models of networks, and there has been Bayesian models proposed for this kind of dynamic formation of networks too. Now, the type of model that we wanted to extend from static model to the dynamic portion was the non-parametric latent variable models, the Bolobus or Hoff or Bickel and Chen type of models, which are actually static models, and we wanted to see them how they can extend to the dynamic version too. And the type of model is very simple. That means this is the latent variable kind of model that we, for each node there is an associated latent variable, and based on the value of that latent variable there is a probability of an H formation in the network. So that's the static part of the model. And so there has been recently there has been a lot of work done on this kind of static models, means where the main parameter here is actually the W parameter here, where rho n is the scale parameter what we can consider, which controls the density of the graph as if. However, in this case usually the W is not identifiable, and it is only identifiable under some measure preserving transformation. So a special case of this model is of course the stochastic block model, where each of the nodes belongs to one of the different blocks or communities, and the probability of H formation between different blocks or communities are different. So that is this is one of the, you can say, one of the special cases of the non-parametric latent variable models. So we wanted to extend this framework to the dynamic situation, and the way we tried to do it was very general, which we found out that it was not really an identifiable system very quickly. So that's why we went to a very simple model of that. So which was that we started with an initial latent variable associated with the graphs or nodes, and then of course the latent variables evolve with time. So there is some kind of a Markovian process which controls the evolution of latent variables with time, and based on the latent variable at a specific time point as well as the another Markovian structure, that means the adjacency matrix at the previous time point, the current edges are being formed. So this is a very general framework, and it is not really identifiable because there are a lot of means it can be easily shown that F and W, they are not really identifiable. But there are various special cases of this model which become identifiable. So like the set of models proposed by Harry Crane, which was based on random rewiring mechanism. This is a special, means can be considered as a special case of this kind of models, and it is identifiable, and he proved the extension of this exchangeable arrays there. And the evolving communities work that was done, that also can be considered as a special case of this kind of system. Here also what happened in there, it was proposed some kind of a mechanism for this evolution of the latent variables or underlying communities. However, this the probabilities were not changing with time, the probabilities of forming the connection. So there are this means some special cases of this model is identifiable in certain situations. So, but we went for a very special case of this thing, what we call, means this has been called in various ways. We called it dynamic stochastic block models, but this has been called in various names in the literature also. So the way we tried to form was that there is an initial or only one community assignment in the network, and based on the community assignment does not change with time, it remains constant with time. However, the probability assignments change with time. That means the networks are formed by with the probability of connecting. The probability of connection between two different nodes depends on the connection probability matrix, and that changes over time. So the connection probability changes over time, but the actual underlying community, that remains constant. So that was the very special case that we considered. So here our goal becomes that there is one underlying community which is structure which is unchanged over time, and the goal becomes that we want to find that underlying community structure which is unchanged over time. But the dynamic portion comes from something what can be said as something like a conditional independence situation here too, but mostly the dependence comes from the fact that the underlying community structure that remains unchanged over time, and the connection probability matrices, they change over time. So that's the very simple kind of dynamic network model that we ultimately focused on, because that's one of the problems where we can first try to tackle, so that we can find theoretically that we can really uncover the nodes, community structure of the nodes. So, so that's the model that we are focusing on. So now, for this model, what we wanted was to develop some kind of a spectral clustering framework for this. Now, spectral clustering methods, as we know, that the main underlying idea is that we try to get hold of some kind of a matrix, which is usually means the number of n cross n, that means the n is the number of vertices in the graph, but it can be of other kind of sizes too. So we try to get hold of a matrix specifically which is a function of the adjacency matrix of the graph, and we do a spectral decomposition of that matrix. We try to take the first few eigenvalues of that eigen decomposition or singular value decomposition, and we do some kind of a clustering on that initial on those singular vectors or eigenvectors, and based on the clustering we get a community detection scheme or a clustering of the underlying graph or network. So that's the idea of general idea of spectral clustering algorithm. We start with a matrix, do spectral SVD or eigen decomposition using the eigenvectors or singular values. We do a clustering to get the ultimate community detections. So, and yeah, this has been talked several times in the workshop too. So now in our case, what we had was, instead of one network, we had a bunch of a time series of networks, we can say. We had a bunch of our time series of networks. However, these networks had one underlying factor in common, which was that they had they had the same underlying community structure in them. However, the connection probability matrices were different, so that means that the networks in itself were different. So we had this host of networks, a time series of networks, and our goal then becomes that trying to find a matrix on which we can do the eigen decomposition or singular value decomposition. So the two different candidates that we considered, this one has already been proposed in the literature, so which is the sum adjacency matrix, that means taking the sum of the adjacency matrices at all time point, and the second is squared of the sum adjacency matrix. There was actually a reason we went for the squared of the sum adjacency matrices, because there was, yeah, we'll see in the theory that there is an intricacy that occurs for the sum adjacency matrix, for which we considered the squared sum adjacency matrices. So these were the two different type of matrices that we considered. So let us try to go a bit detail into the methods. So the first method, as we saw, the main matrix that we are dealing with is the sum of the adjacency matrices for all time points. And once we have that matrix, the sum adjacency matrix, we take the eigenvectors and then do K-means clustering algorithm. And that's the same rule that we saw for the general rule. That means we do K-means clustering algorithm on the top K eigenvectors. Now, one thing I should mention here we are assuming that K is known. Means that is something which is assumed here. Means as was mentioned in one of the talks yesterday, that there is a huge literature on how to estimate K. Some of them can be used here, and some of them have to be used here with some caution, because this is a bit of different setup than the static setup for which usually these methods have been developed, estimation of K. But we didn't consider the problem of estimation of K here. We just considered that we knew the number of communities here. So based on, if you knew the number of communities after K-means clustering algorithm, we have means clustering of this the nodes or the vertices of the graph. So just for going into the theory, some of the details about the parameters and the notations. So the connectivity matrix, which we call here as B, we consider this BT for each of the time steps. The sum of that we consider as B, and the probability matrix, the P matrix, is actually the n cross n connection probability matrix. So B is the K cross K connection probability matrix, which is determining the connection probability between block to block whereas P is the n cross n connection probability matrix, which is giving you the connection probability between node to node, which is just, you can say P is just a blow up of B. So these are the two notations, and some means you can say these are conditions or assumptions that first of all that we have this dynamic stochastic block model which is generating the adjacency matrices. The P matrix has rank A, that means it is a blow up of the connection probability matrix B, and gamma n, which is the gamma n is the smallest non-zero singular value of P, and D is the maximum expected degree. So based on that, what we could prove was some kind of bound on the number of misclassifications in this situation, and so Fi is the number of misclassification for each of the classes, and we try to consider the number of misclassification in the total number of misclassification in this case, and we could get a bound of the misclassification case in this kind of situation where we have for this case of some adjacency matrices. Now for a very if we want to consider the asymptotic situation, the special cases, we can say that if the eigenvalues of each of the eigenvalues of Bt are strictly positive, and of course we have this condition on Td, that means they are of the order of log n. In that situation we have what we are known as weak consistency, that means the fraction of error goes to 0. Now Td is of the order of log n, is where D is actually the what we can consider is something like a maximum degree. We can see that if we have the average or the expected degree or maximum degree of constant order, even if T is of the order of log n, in that case we can still have weak consistency of recovery. So that gives us, as we expected, some kind of more powerful result here than the static cases. That means in the static cases usually the degree has to be of the order of log n in order for spectral clustering to work. Yeah.
But so here you're summing all of the adjacency matrices over time, and then in a sense treating that as a static weighted network.
Yes. So yeah, I am taking the sum and taking that as the static as a static network. Yes.
And then the total quote degree is the total weight of the edges in each.
Yeah, means we are actually dividing that by 1 over n. So yeah, but taking that degree of that weighted matrix as the condition. Yes. So since we are actually dividing by the T, so that the degree is like the degree of the individual networks. Yeah, so it is very similar to the static network models that we have. That means if T was equals to 1, it was similar to the spectral clustering, static spectral clustering results that we have seen. But the main problem with this result is this part of the assumption, which is a bit of a stronger assumption that is usually put in the static case, which is that means each of the this sum of this the eigenvalues of this sum of the Bt, that the B matrix, that is sum of the Bt matrix, that has to be, all of the eigenvalues have to be non-zero. So that is a restriction which is usually not there in the individual situations, but when we are collectively considering them, that assumption has to be put there, because otherwise it becomes the problem becomes that A does not have any community and might not have any community structure anymore. So that's why this extra assumption has to be put there, which is something like we can say that if there was two different connection probability matrices, one was something like a community structure at one point and another point it was something like a bipartite structure. In that case, when I am taking the average of the adjacency matrices after all the time points, they as if cancel each other, and the ultimate adjacency matrix that I have don't have any community structure anymore. So such a situation can happen here and can destroy the community structure. But the community structure is still there. Some of the networks in the whole time series has the community structure, but it got lost when I was taking the average. So that problem might happen here in this kind of when I am taking just the average. So that's why we went for this second situation, that means the squared of the adjacency matrices. So in this situation, that problem can be averted. So we took the square of the adjacency matrices here, and the idea or the method was again the same method. That means taking the square of the adjacency matrices and summing them up, and then doing spectral clustering based on that. And means again based on the same notation, and we using the we have to use this sum of the squared BT matrices and squared P matrices if we consider them, and of course the conditions that they are coming from the same dynamic stochastic block model that we were considering. We also get a similar kind of error bounds here. The number of mistakes we are getting, that we can also prove that we can give a bound for the number of mistakes we are making. Of course, the bound is a bit more relaxed than the bound we got for the the sum of the adjacency matrices situation. So, which we can see that previously the power of the log that we got, the power of the log here is much more different. So, it can be due to the artifact of our analysis also, but we could not make it less than that. This kind of polylog n powers we could not make less than that, at least at this format. And it took and for proving this also we hit several roadblocks, because squared adjacency matrices have not been, especially some of squared adjacency matrices have not been looked that much into the probability literature. So, we had to come up with our own method of proving this result, but using the same structure of proof, but the combinatorial proofs were a bit different. So what we have here is that now the means we can consider the same kind of assumptions which are usually there for static networks, and then say that under that kind of assumptions for each of the static networks, that means each of the static networks has some kind of a non-zero eigenvalue structures. That means the lowest eigenvalue, there is some kind of a separation between 0 and the smallest eigenvalue for each of the networks. And under that kind of a situation, what we can say is that there is a weak consistency in recovering the networks. So, that we can say for a square situation, but of course the rate is a bit larger, it's a bit weaker. And so, the simulation results also somewhat supports the you cannot probably see one of the curves. So, for very sparse networks, actually when you have a distinct community structure, this is the sum adjacency matrix. The sum adjacency matrix usually performs the best when it is a very sparse network in this kind of a search work. But when the network becomes a bit dense, then sparse and the square, the sum and the squared sum adjacency matrix, they perform the same. There is not much difference between them. However, if you try to go for the situations like the situations that I described, that the parameters are in a situation that they can cancel each other in those kind of a situation, you can easily see that the sum adjacency matrix has a qualitatively different performance than the squared sum adjacency matrices. And for the neuroscience example also, we tried to use this kind of method in order to find the communities. And what we found was that we could find, based on the networks produced, some quite a meaningful communities in this kind of a situation, like for speaking monosyllabic words like ba or b or ba, the kind of parts of mouth that are usually used, the lips, the vocal cord, those could be identified as clusters, as proper clusters of that part of brain. So, this was based on observation by the neuroscience, that the clusters that was usually observed, they were coming from the parts of brain that usually controls the main three functions that are usually associated with speaking the word b or ba. And I had a movie on this kind of clusterings but I will just skip it for time. And so, the summary just is that we just consider two different methods of spectral clustering for this dynamic version of stochastic block models, and we try to give theoretical justification for both. But there is a lot of work, this is a very initial framework, we can say. The dynamic block model framework that we considered was also very it's the first kind of first pass, you can say, on the dynamic block models. the communities changing over time is one of the things that should be the next problem that we go for. And also like how to, means under which constraints we can do the community detection in this kind of setup where communities are changing with time, and also communities are changing with time, and along with that, there are this Markovian or some kind of stochastic framework where there is dependence on previous adjacency matrices to which we didn't consider really in this dynamic block model framework. So there are a lot of extensions to be done in this kind of works. And yeah, let me know if there are any questions. Thank you. Yeah.
So I missed how squaring fixes the problem you referred to, where, for instance, if in the first two over steps I have an assortative structure, and in the last two over steps I switch to a disassortative structure, then it seems like you could still have the average of the square of the adjacency matrix being completely flat. I mean, in particular, if the adjacency matrix is zeros and ones, I mean, is this element-wise squaring, or that wouldn't? What am I missing?
So the thing is that
It's the average of the matrix square?
yeah, means average of this is the square a square of.
Okay. But it seems to me that there are examples with like tripartite structure where there you have a similar problem where the community structure is really strong if you look at particular time intervals, but where the average would still be flat.
Yeah, the tripartite structure can still be a problem here. Means, but yeah, means the problem that it tries to fix is the summation problem here. The sum of the B problem that it tries to fix. But the summation of B square kind of things, when we are considering that the B square matrices means at least the community part of that, that means if there are bipartite structure and community structure, it fixes that problem. But yeah, there can be tripartite kind of problems here which still are there. That problem might still be there. Yeah.
Maybe I didn't really understand. So when you construct this method,
You speak up a little bit.
sorry. So when you construct this network and you use partial correlation, I guess the original data is a kind of a high-dimensional time series one. So in order to construct every single network, you need to use some smoothing technique to using a sliding window and then get the partial correlation in order to get every single network. Am I right?
Yeah, so actually the thing is that in this kind of case we had repetition experiments. So we use that in order to construct what we can say the sample size to construct the partial network. So we were not using the window kind of thing, means we were not using previous information or sliding window in order to construct the partial correlations. So since there were repetition measurements, we were just using like means what we were using was Mainshausen-Bultmann method. That means we were taking each of the nodes and we were trying to regress with the other nodes, and the repetition gave us the sample space there.
Okay, so maybe my further question is not that relevant now. But still I want to ask, so if you think this is a stationary time series, because eventually what you are doing is you are just averaging the whole thing. Why not just take the whole time series and construct a partial correlation and just do spectral clustering on the final thing?
Yeah, means we can construct the whole time series, means the whole partial correlation also. But sometimes what happens is that is one of the things also we did. But what we found was that in this kind of a situation, when we were constructing the network separately, it was uncovering the network structure, means the community structures better than that one. So we did both the approaches there. That means constructing the whole network based on partial correlation and also individual time, and then trying to take the networks from there. So yeah.
I think we probably should continue this discussion
And
afterwards.
Yeah.
While we have a change of speakers, maybe we have time for another question.
yeah, so at the beginning you said that the general Markov model you wanted to use was not, well,
wasn't specified, and I wondered if you had examples where two different parameterization was the same sort of network dynamic afterwards. So what sort of confounders can happen?
Oh, means especially the confounders came when when we were considering the Markov framework for the changing of the rewiring, and that Markov framework, and as well as we had a dependence on the previous adjacency matrices. In that case, that could act as confounder. That means it might be difficult to differentiate that the change in the edge formation, from which point it is coming. Is it coming due to the change of the latent variable structure, or is it coming because of the Markov situation that is going on because of the previous edges, connection with previous edges? So that can act as a confounder for the situation where you don't have identifiability.
Okay. Arash, are you ready?
Do you need to?